Let me just actually record, yeah. Okay. So amplitude is displacement of equilibrium. We could also think of it in the case of a wave. How would we define amplitude in the case of a wave? We call it the blank of the wave. For what? I think about like the rope example. It would be the what part of the wave? The height. Very good, Jeff. Well done. The height of the wave. The height of the wave. So the amplitude, again, is the max displacement from equilibrium, or the height of the wave. It can be measured in many units, right? We talked about how it can be decibels for sound, how it's meters for a spring in a mass spring system, and how it's degrees for a pendulum itself. Okay, for a pendulum. So that's the height of a wave. What about the width? The width of one wave. What are we calling that? And we use several terminology for this actually too. Wavelength, right? Wavelength is the most recent one. It's wavelength. And believe it or not, if you plot something as a function of time, it could also be the period of the wave. The period and the wavelength are actually kind of like the same thing. Okay, so to give you an idea, like we've talked about this, where again, this is the action, and I should actually go from beginning to end to show you, but this is the wavelength, and this was the amplitude itself. But the word period could also be used if, for example, this were x as a function of time. If I was plotting a graph where x displacement of something is a function of time, then the time it takes to complete one cycle we call the period, right? So this could be called wavelength, or this could be called tau. I could call it the period also in this case. So it's important to recognize that, and we picked up on this actually, if you've noticed, that the actual period was defined as 1 over the frequency. Right, it was defined as 1 over the frequency. But we also had this other formula that said this. We had this formula as well. And if I look at this formula, right? If I look at this formula and solve it for lambda, remember this symbol, the wishbone symbol? If I solve this for lambda, I get lambda equals V over omega. Lambda equals V over omega. So what I'm noticing is this, and take a look. The period and frequency are inversely related. But so are the wavelength and frequency. And you saw that in your lab. You proved that. Remember with the string? You recognize that as you increase the amount of hertz, the frequency, hertz is the amount of cycles that occur every second. So if more cycles are occurring every second, it means the waves have to be much shorter. So wavelength is inversely related to frequency, as we saw in the lab, in lab 12. But period is also inversely related to frequency from section 13.1, 13.2. That was our definition. So what it looks like is that period and wavelength are very similar things. But the period is the time for one wave to occur. Wavelength is physically the length of that wave in meters. Okay? It's just a matter of units at this point. But they're both similar in that nature. So here's another important formula. V equals lambda omega. Lambda, again, wavelength, omega being frequency, V being the velocity, or in this case, really, the speed of the wave. Okay, the speed of the wave. The direction doesn't really matter. So we use V as a variable here, but we're really talking about speed in this case. We had two other formulas from the first section. We have tau equals 2 pi root L over G. And then the second formula we have here, tau equals 2 pi root M over K. These aren't in formula sheet, but just to reference them real quick and to use them. We talked about their analogous nature, and I've discussed the idea of the numerator being a parameter of the actual setup. So L stood for what again?
Length.
Of the
String.
Good. Length of the pendulum string, the cord, whatever you call there, good. And M, though, was the mass of the actual system on the spring, whatever's hanging from the spring. So this is the pendulum, this is the spring. But L and M are simply characteristics of the setup. It's a length, that's a measurement. It's a mass, that's a measurement. It's a parameter of the actual apparatus that you're using. Whereas the denominator is not. Well, it kind of is. Half and half. G is a function of the planet you're on. So when we're on Earth, G is just 9.81. For another planet, you can actually solve for G. You guys did that in the lab, right? You have to prove G. In fact, actually, some of you might not have gotten to it yet. This is why Lab 11 is actually very useful for the test. That's why they make you do it until next week, so that over the weekend you really do practice it. So if you're not sure about something on the lab, you want to ask me, an email would be good for that. You know what I mean? Or at some point today you can ask me about Lab 11. But there was an example in Lab 11 that had you calculate the value of G based on your timing of the pendulum. It was toward the very end, right before the discussion questions. That's a really good, useful example to think about for the test. Because you could figure out, and I've talked about this with some of the groups I mentioned it, if you go to an unknown planet, literally, if you were somewhere, and I know this is very hypothetical because you're not going to probably do it, so you're probably saying, what, but it's kind of cool to think about, is what I'm saying. You could be somewhere completely unknown and have a stopwatch and a ruler and some sort of like a cord, physically like a length of cord, and you could figure out gravity. You just take the time it takes when you measure the length of the actual pendulum, you could solve and figure out gravity on that planet. So when you, like, people have asked questions like, how do you know gravity is 9.81? And we showed it with a picket fence, but how did scientists figure it out a long time ago? That's quite simple, right? So think about like something like a time turner was used, something that can actually report sand before clocks were been discovered. And the length of measurement, well, the length itself, it's arbitrary. We use the term meters. That's why it's 9.81. Right? When it's in feet, it's 32.2 feet per second squared. So again, that changes based on whatever unit the scientist was using at that time. But proving that you could find any gravitational pull from just having these two things. K, very similar to gravitational pull, provides the restoring force. K is the spring stiffness, it's the strength of the spring. So when you stretch the spring, it wants to pull the mass back. When the spring then gets compressed by the mass, it pushes back. And then the spring gets pulled, it pulls back. So every time you have some sort of an action, the spring responds with the opposite action. So that's why in the lab, if you recognize when you were calculating your K values using Hooke's law, you were solving for K by figuring out that, you know what, Fs in that problem was the spring force. And that was provided by gravity. We'll draw that. In the lab, we saw that gravity pulled down on the actual spring, and the spring pulled back up. So that was our free body diagram when we did the lab. And you guys literally had the mass that was attached to the spring that kept stretching it further. So Fs and Fg were opposite directions. Well, in that lab, if you recall, the displacement of the spring was down. It was being stretched downward. So the displacement was downward. So I put X there, you put Y. Just because it's F equals Kx, I'm using X. So in that formula here, we can recognize that if we want to solve for K to use in this formula here, we can do it by figuring out what the spring force applied is and how far it's been displaced. K must always be what kind of a number? K must always be what kind of a number? I'm alluding to this example. Think back to the lab. A couple of you had this question, that's why I'm saying it. K must be what kind of a number, not what number, what kind of a number. Positive, very good. Okay, K is a characteristic of the spring. So in the lab, we recognized that the X value, the displacement, was negative because it was stretched downward. The spring force was positive, that was pulling upward. So we have a positive here, a negative in for X, and then that cancels with this negative right here in the front. The double negative leaves K behind as a positive value. So solving for K, the spring constant, based on data like you did in the lab, is something that you should be more than ready to do on the test. Okay? So given some sort of spring force table with displacements, being able to figure out K, and then utilize K to figure out maybe a period or the mass of an object based on a system of spring oscillating. So yeah, gravity we talked about already, but gravity is like K, it's a restoring force. These things are very similar to each other. Okay, recognize the analogous nature. Gravity is what pulls the pendulum back to the middle, right? Gravity pulls it to equilibrium. Every time it passes equilibrium, gravity pulls it back. Every time the spring passes equilibrium, the K value is what's pulling it back. So the denominator is the part that's responsible for the restoring force. Let's see. We talked about the difference between transverse and longitudinal waves. It was the beginning of the segmental waves. And there was one real characteristic that was different about the two. It was the one characteristic between transverse and longitudinal waves that made them different. They can both be plotted with the sine curve. We can both look at them with some sort of displacement curve. What was the major difference between them?
Transverse perpendicular and
Yeah. So transverse has the letter T in it to remember that. And what do we mean by this? What do we mean by perpendicular and parallel? What do we mean by perpendicular and parallel? You're right, those are the terms we're going to use. But what is perpendicular? What is parallel? What's happening here?
I think of perpendicular is like one's going to be going left to right and one's going to be going down. So,
Well, what do you mean? You said one's going to be doing that and one is going to be doing that. What is one?
waves.
Okay. Waves. All right. Anything more than that? You want to elaborate?
Yeah, it's the applied force in the waves perpendicular to the force, and then the other logical there, the direction of the force.
No, not the applied force, but I like that. Because the applied force actually, like if I apply force like this, right, that's up and down. That force and all those waves move up and down actually. And then when I apply force like this, they move like this. So no matter what direction you apply the force, the wave will move that way. So that's good to know. But there's something else. The oscillations of the wave and the actual wave itself. So the wave that we send, and we looked at two examples, with the slinky, we looked at those two examples. One of them, the wave traveled like a percussive nature. You popped it like that, and the wave literally was moving left to right. And the vibrations were occurring left to right in the slinky. Whereas the second time, the vibrations were occurring up and down, yet the wave still carried left to right. So when the vibrations are up and down, but the wave is propagating left to right, that's a transverse wave. This is showing the vibrations up and down. This is showing the motion of the wave. Whereas the longitudinal wave, the actual vibrations are in the same direction as the motion itself. The example for the longitudinal wave, if you remember, was when you're standing online at a store and they let 10 people in the store. I gave the example of like everyone's going to move up a little bit. That's literally everybody compressing and decompressing, compressing and decompressing. Arrigo, sorry, go ahead.
Does this transverse wave, the displacement goes up and down, but for the longitudinal wave, kind of goes back, and then goes back?
Yeah, I wouldn't use the cyclical motion, but it goes like forward and like stops, and then forward and stops, so the compression of the actual wave is moving this way. So it's like wave fronts.
But is it like compressed?
So the idea, the example that we gave was that the part of the spring was compressed, and that compressed part would move along the actual slinky itself. So when you had a part that had high density of compression, that was like the peak of the wave. And then when it was low density, when it was like expanded in that part, it was a low density. So that was like the trough, the bottom of the wave. So the nature of the wave, when you look at the actual plotting, is always going to be like this, right? So no matter what, either wave, it's going to have the same actual characteristic. But what I'm saying is that this is a measurement of vertical vibrations, whereas this measurement is a measurement of horizontal vibrations. But the wave itself actually looks the same in both cases, because this is measuring how far the slinky was moving up and down. This is measuring how much the slinky is moving like this. And different parts of the wave have different densities along regions. So like think about the people online, right, when they move. Say there's a gap opened up to the door, and everybody starts walking together. So in the beginning, there's going to be a little space behind me. And then the person behind me is going to catch up. The person behind them is going to catch up. So what's happening is the wave is spreading out and then condensing, and then spreading out and then condensing. So that's a longitudinal wave. That's like the wave we talked about with sound waves.
Does the longitudinal wave expand more, or is it always like the same size and it goes like this, while the other one just keeps expanding?
It's not about... So this one is not expanding over here. This one on the left is not expanding. This has to do with it vibrating up and down. The molecules are physically vibrating. That's why when we use the slinky, we went like this with the slinky, and the wave looked like this the whole way through, and measured the vertical vibration. When you go like this and send the wave that pulse, it's about where the compression
This
is.
is just a pulse, right? Just like
An example is a pulse. Yeah, so this is literally one pulse. This is like that pulse moving through. So that pulse has compression here, and then on the other part, there's expansion on the next part. And then the slinky will actually carry that wave back and forth. So this will propagate that direction. But this is not a measurement of vertical vibration. This is a measurement of how much it's vibrating this way, I suppose. So the actual graph looks similar, but they're not the same waves. Let me try to think of another example, and I'll come back to it if I can think of another way to explain it. We talked about damped motion. I've used that phrase a lot. What do I mean when we talk about damped motion? Why do we talk about this? What's the realistic nature of damped motion? Chris?
Isn't like damping or dispersion of energy?
Yeah, it's literally just like getting rid of the energy in the system. It's exactly that. So when you think about a mass spring system, the actual spring stores energy when you actually pull on it, you let go. Well, eventually that energy has to get dissipated in some sort of energy loss, and the spring will come to rest. So when we think about dampened motion, what would a graph like that look like? What would a graph look like using, again, a wave, but a wave that has damped motion? What would that wave look like? Very good. Well done. It would do something like that, yes. Okay? It's a wave that starts large, and literally its amplitude gets smaller and smaller and smaller. The rate at which its amplitude gets smaller can usually be modeled by an exponential decay function, actually. Take a look at what I'm pointing to here. If I actually take my pen and draw an exponential decay function, it actually models this perfectly. An example of this, if you're not sure what we're talking about besides the mass spring, would be the oscillation of your car after hitting a speed bump. Think about when you hit a speed bump, if you're driving your parents, you slow down, you hit the speed bump, and your car oscillates and then it settles out, right? It settles out pretty quickly. So we hope that this oscillation or this minimization of the oscillations occurs rather quickly. If it occurs too fast, it's called an overdamped system. If it occurs too slow, it's called an underdamped system. If it occurs perfectly, it's a perfectly damped system. Okay, so systems can have levels of dampness to them. Overdamped simply means that it stops oscillating too quick and you feel that jolt on your body. Where if it doesn't if it oscillates forever and you see something like hit a speed bump and it keeps going up and down, it means it's underdamped. But the phrase is something that's important for sure that we've talked about. Let's see. James, you had a hand up for a second. What were you going to ask?
It's called a damp system.
Damped. D-A-M-P-E-D. You could say the oscillations have been dampened, but you say it's a damped system.
And in the end, it's just a flat line, right?
Yes and no. I mean, theoretically, yes. But realistically, I mean, it eventually stops, but the particles themselves are still moving, so it never really stops, you know? Because it's going to sit there and oscillate. Even a pendulum that would eventually come to rest, it's going to have like any little disturbance along the way, but eventually it would become a flat line. Yes. Yeah.
If you leave a pendulum like moving in space from the vacuum, is it going to move forever?
In a vacuum, absolutely, yeah. Yeah, it will. Because you're not going to have any energy loss along the way. I mean, you have probably some frictional losses wherever it's attached. Like this example that we did, did we do it in this section in the other class? It was here, right? Yeah. When you attach it at the top, it's a metal eye hook, and the actual other piece is metal. So between the actual parts, I could see there being possible friction. So it'd probably go way longer, but maybe it eventually would stop if there's enough friction. Say again?
If it's like magnets, so it doesn't touch,
Yeah, then I guess it would. But even that, I guess, yeah, in a vacuum it wouldn't matter. It has to be in a gravitational field. So on Earth, in a vacuum, it wouldn't be in space, because without gravity, it wouldn't swing, right?
No, but like if you force it.
If you forced it, it would just continue around, though. It'd be in circular motion. There's no gravity in space. But no, in a vacuum on Earth, you can create vacuums, just remove all the air. In a vacuum on Earth, theoretically, yeah, maybe it would, especially if there were a magnet that was levitating it. That's the idea behind the maglev trains, right? The maglev trains is very low friction because there's not really much contact between the actual train and the track that it's on. Has anybody traveled on those? Right in Japan, is that where the maglev trains are? Anybody know about maglev trains? We maybe talk about them a little bit. I had a professor actually who did some research in the area. He was really smart. He was my thermal fluid teacher in like sophomore, junior year of engineering. And he was here from China studying for the last 7 years. And his research paper was on, and this is kind of cool. Remember we talked about modeling? This is really kind of cool. He modeled skiing and looked at what's called this, what is he called? He used to use this phrase all the time. This incompressible layer of pressure between the actual ski and the snow as being analogous to a maglev train. If you've skied before, if you're watching the Olympics and seen downhill skiing, they're skiing at like 95 miles. Did you know top speeds of 95 miles an hour in downhill skiing? It's incredible to think about how fast they're going. And then they have to take turns. Now, I can imagine the amount of like force of friction they need. Literally, think about that. The skis need that much friction to stay in that kind of a circular path because there's going to be so much centrifugal effect of the skis to want to slip out that you need to literally carve. You heard the word carve before with skiing and snowboarding? So anyway, he studied the maglev trains and actually compared skis to maglev trains and the conditions that they both undergo, being the same thing, being about the same thing. And actually, it's pretty amazing what you can see when it comes to them. Again, it's just modeling. He just took one idea and modeled it to the other and studied the mechanics of skiing and applied it to that. Let's see. We talked about destructive and constructive interference and superposition. What was the idea? Can you give me a quick summary of destructive versus constructive interference and how that relates to superposition? Can you give an example? Tell me about maybe like a graph example if you want, or a physical example of something that occurs with destructive or constructive interference. No? Superposition was the summing of two waves' amplitude. I'll give you that part. Superposition was taking the amplitude of two waves and being able to sum them together. Sum them together.
With constructive interference is when two waves moving towards each other and they add together.
Okay, good.
And destructive is when they're going.
They're still moving this way. Keep going. But what do they do instead?
I think they're going in opposite direction. The one is on top, one's on the bottom.
And then what happens in the middle?
It's a smaller wave.
Yeah, so the idea is that if a wave has a negative amplitude and it coincides with another one, the other wave has a positive amplitude, they'll actually cancel each other out. It's the idea of destructive interference. The physical example of that I gave you was literally like water in the ocean. And if you've seen the wake behind one boat and the wake behind another boat, when those wakes come together, wakes look like little peaks, right? You ever see like the wake and the water moving? Like what occurs after the boat passes? The wake will literally travel until it gets together, and then you'll see a big wake, and then they'll pass through each other and continue. That was the physical example of it. And then graphically, I gave you guys an example with like three different waves. There was like a red one, a green one, and a blue one. And it was the blue and the green that added up to become the red. But that was the concept graphically of superposition and constructive and destructive interference. If two waves cancel each other out, it's destructive. If two waves sum together to make a third wave that is larger and they're all positive, it's constructive. Or if they're all negative, it's still constructive. But if somehow two waves sum together to make a larger in amplitude wave, it is constructive interference, okay, versus destructive interference.
Is amplitude always positive?
No, that's what I'm saying. So what I'm saying is if you have negative amplitude and a positive amplitude, that's what destructive interference is.
But you said if it's two negatives, then it would be a larger amplitude.
And that would still be constructive interference, but it would be larger in the negative direction. I mean in magnitude, right? I'm talking about the height of the wave. So when I say amplitude, the amplitude is the height of the wave, whether it's positive or negative, really. But you can think of it as a negative number because it's going down. It's actually the peak is going down.
So if they're opposing each other, it's destructive. If they're moving together, it's constructive.
If they're both on the same side and hitting together to become bigger, constructive. If they're on opposite sides and they cancel, destructive.
Okay.
They could be both on the bottom and it's still constructive. Top or bottom, they're both constructive.
Okay, so
as long as they're both the same amplitude side.
So we don't, like, for superposition also. Like you said,
Superposition is, if you can do constructive and destructive interference, that's what superposition is, really.
Oh, it is.
Okay, it's the summing together of two waves to create a third wave.
Does the frequency of the waves change anything with that problem?
So, yes, if the two waves have different frequencies themselves, they will be affected. But if they have the exact same frequency, then it won't. Like if they're passing through one another with the same frequency and they have different amplitudes when they have interference.
They would just have each other.
Correct, in amplitude. In amplitude.
Like what if when one is going down, the other one's going up?
So
What happens?
superposition isn't even about two different frequencies. It's just about amplitudes that we're concerned with. Yeah. So when you have combinations of different frequencies, you can get waves that result as a combination of those two. But it's not going to be like you're just going to sum those values together. It's not the same as superposition where you add the two amplitudes and you're going to like add frequencies. You see what I'm saying? So you can't make the same assumption. It's not going to be like you can extend the idea of superposition into frequencies also in addition to just amplitudes. Let me do a math example. So we talked about the kind of one you could expect for springs, right? Being able to work with Hooke's law for sure, and then being able to use that to calculate something to do with period. Let's see, we have a couple of the formulas to recognize, and these are ones that I think a couple of you have had a little bit of difficulty in solving. So in a formula like this, being able to solve for one of the variables that's inside of the radical is important. So whether it's L or G, what approach would I take for a problem like this? We want to solve for either L or G. Chris, why don't you step me through?
You divide 2pi over.
I would agree. And again, it's not the only answer what we're saying here, but I would take this route personally.
And then you put in parentheses and you square it, and then you multiply the denominator over to the left side. You can solve for the top variable or the denominator.
Very good. So Chris is saying the last step here, multiply by G. Multiply by G, we get tau squared G over 4 pi squared. That would be the length of the pendulum itself. Or you could solve for G. How would I solve for G? I would just take G right here and flip it with this entire thing if you want. Take the entire fraction, move the entire fraction into the denominator, move G up here into the numerator, and you get G by itself. The common mistake I keep seeing is that people try to divide by L. And then you're left with 1 over G, not G. Is that clear? If you divide by L here, which a lot of you have been doing, I notice, can't divide by L here, or else you're going to get 1 over G. This is in the homework, and then also when I was going around looking at your lab when you're solving for G here, make sure to move that G up and the whole thing down below. Yeah, Rick.
So if the problem doesn't tell you that G is 9.81.
Correct. If it says you're on an unknown planet, what do you think you're going to be doing in that problem? Probably solving for G, unless I say where gravity is 6 meters per second squared. Then you use 6 for G there. You follow what I'm saying?
Yeah.
So it's got a preface with an unknown planet, or a planet with gravity this. But if it doesn't specify, G is always 9.81. Yeah?
Is the homework for 15 grade 4 due tomorrow?
Tomorrow.
Yeah,
I think it's at like 3 o'clock tomorrow for you guys, yeah. But some people submit their homeworks early. So
Yeah.
I always look at your homeworks, yeah. Let's see. In the other formula, it's the same thing with m over k, right? The solution process is absolutely identical. So if you're trying to find k or m in that formula from the other one where it's 2 pi root m over k, you would do the exact same thing as this. You would still divide by 2 pi, but this would just be m over k, and that would be m, and that would just be k. And then if you wanted to get k by itself, you could just put it here and take this whole thing and move it down. There was one other formula we talked about, and that was the one that we mentioned earlier. And there's not much I can ask you about mathematically with this, besides know how to use scientific notation. These are like 3 points, provided you do the right work. And last test, that wasn't the case. Okay, you had to work with masses that were on the order of 10 to the 7, and a lot of people made mistakes in the calculation step. The math, for the most part, the theory for the most part was right, but the calculation was incorrect. So when we're working with stuff that's in scientific notation, A, we need to know our prefixes, and B, we need to know how to enter scientific notation in the calculator. Those 2 things. So what do we have for prefixes that we should know for this? What are some prefixes that we've been using? Yeah, centi for sure. Centi's 10 to the negative 2. If you don't know these, in your calculator, there's a thing that says a unit converter and stuff too. There's stuff with unit conversions in one of those apps. So I know it's a waste of time, honestly, if you don't memorize them. You have to spend the time now looking it up in the app. But on your calculator, there is a thing with a unit converter, actually. Okay, so you could look at that too. Centi's 10 to the negative 2. Milli, 10 to the negative 3. Micro, 10 to the negative 6. Nano, 10 to the negative 9. Those are the small orders we should know. And then the large orders are kilo, 10 to the positive third, mega, giga. I wouldn't even go to tera. I'll leave it there. Okay, for now, no need for tera. So these are the ones that you might see on your test, so be aware of it. Okay, if it's a frequency, you'll probably see something, little hint. A frequency is something on this order, with a bigger end. Frequencies are large numbers. Wavelengths are traditionally rather small numbers. You can see a lot of small wavelengths. Wavelengths of the EM spectrum, I don't even think they go beyond a couple meters. I'm not sure what the largest wavelength on the spectrum is. We'll see that in the next section when we get to that. But just so you're aware of that. Frequencies are very large numbers traditionally, and wavelengths are usually smaller numbers. Yeah?
What's the difference between the two ends?
Sorry, so one is a lowercase. That's a lowercase at the top. Is that better? And the other one's a capital? This is a capital M, and that's a lowercase m. And that's a symbol that says mu.
Oh,
Remember that? Remember the friction symbol?
And that one's micro.
Yeah, that means micro, yeah.
What is it used for?
Micro. So like micrometer. Micrometer is another word for it. Micrometer. So it looks like, yeah, you can extend it a little. Is that better? Does that make it more? You can see it better with that, right?
Yeah.
Extend the bottom.
No, I just thought the M and the U, what you saying?
Yeah.
That's
So M is for milli and micro, and mu is for micro. M is for milli, mu is for micro. And then N for nano. N for nano. What questions do you have on the problems that you struggled with? Chris, go for it.
Page 40, question 80. I just wanted to know if you divided by like 2 or 4.
Do you happen to have the problem just so you can read it, or I'll grab text? Grab the text right here. Page 487, number 80. A large pendulum, bless you. It says a large pendulum swings in the lobby of the UN building in New York City. The pendulum has a 91 kilogram bob and a length of 22.9 meters. How much time does it take for the bob to swing from max displacement to equilibrium position? Okay, so let's talk about that. That is a quarter of a cycle. So here's max displacement right here. Here's equilibrium right here. So when it swings through equilibrium to the other one, that's a half cycle. When it comes back, that's now a full cycle. So when you only go to equilibrium alone, that's going to be a quarter of a cycle from here to here. So you would get the tau value, the time period, divided by 4. Good question. Hey, a couple of you made this mistake in the lab, and I corrected your lab group, so make sure you recognize that. A cycle is through equilibrium and back to where you started. It's the same thing for a spring. You pull on the spring, you let go, it passes through equilibrium, it comes back to where it started. That's one cycle. That's one cycle. Yes?
Number 42. Should we just 475?
Number 42. Let's see.
Yeah.
Okay, let's see. A wave oscillates 5, so this is page 475. Number, you said 42, right? 42. A wave oscillates 5 times a second and has a speed of 6 meters per second. So 5 oscillations per second. That's what I think of right away. I don't know what that is maybe, but I can write it down at least. And then I'm told it has a speed of 6 meters per second. So I know that that's going to go for V in this case, in the formula we've been using. So the question is, what is that 5 times per second? 1, 2, 3, 4, 5. Literally 5 oscillations in 1 second. What is that representing? What has a unit of cycles per second? Or oscillations per second? What variable is that? Frequency. So that's the frequency, okay? And the way you can tell is when you see cycles per second or oscillations per second, that's frequency. When it gives you the time, that's the period itself. So this problem says to figure out, it says what is the frequency, what is the period, what is the wavelength. So we can start with, first we have the frequency is given, so that's the first part right there, that's A. And then it says what is the period? Well, the period is just what? What's the period always compared to the frequency? It's very easy to do it. 1 over that, thank you. So the period is simply 1/5 now. And that is units of seconds. And that makes sense, right? Think about it. 1 cycle takes 1/5 of a second, so 5 cycles happen every second. It makes sense, these numbers. That's part B. And then part C said, what is the wavelength? And to find wavelength, we have to use V equals lambda omega. We're looking for lambda in this case, so lambda equals V over omega. So that would just be 6 meters per second over 5 oscillations per second. So 6/5. Okay? And that'll be in meters, the units.